In the first lecture, I didn't really talk about textbooks. It was my intention to, but we were talking about other elements of logistics. That textbook, Davey and Quinn, is a very, very good supplement to this course. I draw some materials from it, but to be honest, they follow the same kind of logic that I would follow in delivering the course, and so it's the best textbook I've found for intro to hydrology. I provide all of the materials that will help you with your labs and with the test, which, to be honest, for this semester is not as onerous as it has been in the past. So you can get away without the textbook, right, if you really want to. But if you want to do really well in this course and really understand what's going on, I would suggest it's a good investment. So chapter 2 of that textbook follows today's lecture, and also there's a lot of extra information on the USGS website there. Okay, so let's start with how do we get moisture into the atmosphere? So this is an interesting statistic. Around about 72% of all of the sun's energy is converted into latent heat, not into sensible heat. Right? So we often think of energy coming from the sun as heating up the Earth's surface, which of course it does, but only 28% of that solar radiation that is absorbed at the Earth's surface is used to raise the temperature of the Earth's surface. The other 72% is actually used in latent heat transfer to convert liquid moisture on the Earth's surface into water vapor in the atmosphere. And so therefore, by doing that, that's how solar energy moves moisture into the atmosphere and then allows it to be distributed around the globe. That's, maybe some of you already knew that, maybe you remember it from 2300, but it's a very important little factoid to remember, is that most of the sun's energy absorbed at the Earth's surface dries the water cycle. Most of it does not raise the surface temperature. It does, but most of it is actually the heat pump or the engine to move water around the atmosphere. Okay, so now, again, this is just drawn from 2300 weather and climate, so this is really just revision. So let's take this kind of global concept that a lot of that energy from the sun distributed around the globe is driving our climate system in two ways. One, it's putting moisture into the atmosphere. Two, it's heating up the Earth's surface, differentially, of course, right? Because most of that energy is in the tropical zone, just because of the angle of solar inclination overhead. So most of that energy is in the tropical zone, varies daily with the Earth's spin, varies seasonally with the Earth's tilt. Okay, remember all these things from Geog3400 as well. So there's a lot of natural distribution of incident solar radiation over the Earth's surface. But in addition to that, we've got atmospheric circulation, which redistributes heat and moisture around the Earth. Now, when I say heat, I don't necessarily mean sensible heat. Right? I'm also referring to latent heat, or the heat that's trapped in moisture. So that's how the atmospheric system, or the global atmospheric system, is how we redistribute heat in both of its forms, sensible and latent, around the Earth's surface. So some of this is quite deterministic. We understand it at a macro scale. Right, so lots of energy in the equatorial zone. This sets up differential heating patterns, which drives the trade winds or these the north and south polar westerlies. Right, so this is set up by the Earth's rotation and differential heating. Now that means we've got zones of uplift in the atmosphere, and we've got zones of air mass descent, and these are quite systematic, and these lead to these different regions of the Earth. So in the equatorial zone, for example, we have persistent low pressure because of air convergence at the ground level, air mass rising. So we've always got a tendency for low pressures in the equatorial zone. But when we get the Tropic of Cancer and Capricorn, these Hadley cells, they rise in the equator, move poleward, and then they descend. Those areas of descent are characteristically high pressure zones because the air is sinking and pushing down. So it's systematically high pressure. We're not getting into moisture at the moment, we're just thinking about the air mass movements. Okay, so these are quite systematic. This is just part of the Earth's rotation and natural energy distribution. But clearly it's a little bit more variable than that. Right? Those are the systematic elements, and then on top of these systematic elements, we have the more stochastic or random elements where we get weather variations. Okay, let's start to look at some of these variations. So on the right here, these are just global latitudinal variations in precipitation, evaporation, and then the transfers of heat, latent and sensible heat, across those latitudes, or meridional transfer. So first of all, let's look at precip. We see that by far the highest amount of global precipitation occurs in the equatorial zone, right? And we knew that. So somewhere on the order of 2,000 millimeters per year, more or less. And then we see a couple more peaks in these kind of poleward areas of the tropics, like Tropic of Cancer and Capricorn. But the interesting thing is we see these drops in precipitation in those zones, the tropics of Capricorn and Cancer, and this is because of heavy cell descent, air mass descent. So these are areas of systematic high pressure. So we're not seeing as much precipitation there. Now we're just describing characteristics. We're going to look at some of the processes underlying this in a minute. Now, when we look at evaporation, we see that if we look at the mean, it kind of flattens off across the tropics. So whereas we see massive precipitation in the equator, and we have the most energy receipt, it's pretty hot there, lots of energy, we don't necessarily see a peak of evaporation there, despite all of the energy. Can somebody suggest why that is? Why we don't see increased evaporation at the equator relative to the adjacent tropics? At one level, it's counterproductive, or it's counterintuitive, because we know there's a lot of energy there, but that excess energy is not resulting in extra evaporation. Does anybody think why?
Could it be from all the vegetation? It's like keeping the ground cooler.
Yeah, locally that could play a role. It could. I'm thinking more globally. There's something systematically happening in the tropics, and it relates to the first graph at the top there.
It's always raining, so it's usually like there's always a fresh sun.
That's it. The air masses are already saturated. Now, this is a concept we're going to deal with in about 3 lectures time. We're going to look at evaporation. And there's this term known as potential evaporation and actual evaporation. So if we look at the tropics, or the equator in particular, the potential for evaporation is very high because there's a lot of energy. However, actual evaporation is much lower than the potential because the air masses are already saturated a lot of the time. And the reason they're saturated is because, well, there's a lot of moisture in the atmosphere, it's raining a lot, and a lot of evapotranspiration from vegetation anyway. So if you've already got a lot of saturated air, you just can't add more moisture to it. Doesn't matter how much energy is available. That energy is not going to allow more evaporation if the air mass is already saturated. So that's where we see the evaporation signal kind of flattens off in the equatorial zone. Okay, so that's kind of a global latitudinal picture. Obviously, it varies a lot as we start looking at more regional, continental scales and below. So, and here's an example: North America, something we're all fairly familiar with here. But you might actually see similar kind of patterns across Europe and Eurasia. So, what do we see? We see zones of precipitation here and here, dryness here. Does somebody want to explain for me those kind of characteristic patterns and what's driving them? Or any one of those zones of high precip, why are they occurring where they are?
The mountains.
Yep, the mountains. Why is the mountain driving precipitation on the west coast?
Would it be because the wind carries moisture and then it loses moisture on the mountains?
Yep. Right. So we're in this kind of northern, between the tropics and the poles, the northern temperate zone. So we've got characteristic westerly winds. So the weather, not talking about climate necessarily, but the weather's coming off the oceans here. First thing it's going to encounter are these mountains, whether the western seaboard or the Rocky Mountains, BC Coast Mountains, or the Pacific Coast Mountains. That's the first thing that we're going to see. Okay, now remember back to Geog3400, we could go into the orogenesis and why there are mountains there and all that kind of fun, but this is hydrology, so we're not necessarily going to dig that deeply. But anyway, we know there's mountains along the west coast here. And so that's the first landmass that a lot of these air masses encounter. So the air masses are forced up, and then that drives precipitation. Now, I haven't yet asked why would air mass lifting drive precipitation. That's what we're going to get to in a couple of lectures' time. But just bear in mind, Mountains here means increased precipitation. Dryness over here is a result of precipitation being lost here, right? And so there's less moisture in the atmosphere by the time we get over here, because most of the weather moves westerly or from the west to the east. A little bit different here though. What's causing all this high level moisture? And it's a little bit, it's interesting that we've got most of the moisture here. And well, here, it kind of reduces as you go up this way. My hand is kind of giving you a bit of a hint.
Recirculating ocean.
Yeah,
And the Gulf of Mexico.
yep. So what kind of weather systems do we have coming in off the ocean then? Hurricanes, yeah. Tropical storms. In general, a lot of cyclonic activities. Right? So we have a lot of cyclones wheeling across the Atlantic, and they hit land over here. Unlike on the west coast, we don't have big mountains to, to dump all that precipitation off. Yeah, it's hilly in some parts, but it's relatively flat compared to the west. So these weather systems can come inland and take a lot of that moisture quite a distance. Particularly the hurricanes that wheel up this way. And if they run along the coast, they're actually picking up moisture on one side and dumping it on the other. So when you get a hurricane that tracks up like this, or any kind of tropical storm system, it's systematically picking up and dumping. And so it can add a lot of moisture for quite some distance inland along the eastern seaboard there. So, very different hydroclimatological processes, and it's due to the interaction of the oceans and the landmass and the topography as well. So all of these different processes play a role. But bottom line, where ocean meets land, you're going to get precipitation. And the more inland you go, the further you are from your original source of precipitation. And so therefore it's going to rained or snowed out by the time it gets there, and air mass is going to be somewhat dry. Hence, that's where we are in the prairies, relatively dry part of the world, where in any given year, the annual precipitation and the annual evaporation might actually be pretty close to one another. That puts us pretty much close to being on the definition of a desert. It's not really a desert around here, but we're not that far up. Convective thunderstorm activity is quite common in this part of the world. You spend some time living in Nova Scotia, and yeah, you'll get the odd thunderstorm, but not the kind of crazy big convective storm cells that we get here. So that's an important driver of precipitation in the prairies in summertime. Okay. Yeah, so we've got frontal activity, air mass mixing, and the mountains play a big role. So there's a number of components in our regional climatic system that are fundamentally important in driving the precipitation or the evaporative processes in this part of the world. We'll talk about the evaporative processes later. Now, here's this, I think it's a 30-minute video sped up, of course, over Waterton last weekend. And there's a couple of things I want to point out here, and I want to see if anyone can explain what's going on. Just look at the clouds, play that again. Look at the clouds and look what they're doing over the top of the period. Okay, now there's two things I observed from that. Two things happening to the clouds over that 30-minute time period. Now also notice the sun is over there, and this is Waterton Lake. So it's evening time. Okay, so it's 30 minutes around sundown, or just before sundown. And there's two things you can see happening with the clouds, or at least two things that I think are important.
It looks like they're forming over the lowest points, so in the valley, like down Margin Valley, down to the lake. And then as they hit those eastern mountains, like or on the glacier side, as they move east, they're dissipating again and probably reforming the next valley over.
Exactly, that's one very important thing. So it almost looks like the clouds are sitting there, but because it's a time lapse, you can tell the air is actually blasted through there. So the air is not sitting there, but the clouds kind of are, and they're sitting between the mountains over the lake. Okay, so that's the first observation, and we're gonna dissect that observation in a minute. Second observation relates to the fact that it's evening time. What do you notice happening to that kind of clump of clouds over that time period? I'll play it again. Okay, look at the start and look at the end. Okay, it's a little bit more obvious now.
Sorry, that declination.
Yeah, they're growing, right? The condensation of clouds are actually growing over that half-hour period. Let's deal with that one first. Okay, so anyone online, anyone in class, just shout up if you think you know why. Why, at the end of the day, just before the sun goes down, are we seeing the clouds build? Like if I'd have started this time up maybe half an hour earlier, it would have been clear blue skies. But we're going towards sundown, it's getting later in the day, and the clouds are forming. Can someone tell me why that is?
Since the temperature drops after the sun goes down, the water in the condenses, so as it gets colder and colder, it's more and more.
Exactly. The ambient temperature in the air mass is getting cooler. So this is fundamentally important. We're going to look at why that matters in a minute. But when you see a drop in temperature, we tend to see an increase in cloud cover or an increase in condensation in general, or a shift of water from the vapor stage to the liquid stage because the air temperature is dropping. So that's the first thing. The clouds are building because the atmospheric temperature has dropped a little bit.
A nearby lake.
Well, the lake is definitely playing a role, right? So there's a ready source of moisture there.
Is it the solar energy that's being emitted from the lake from the day? That's like the surface temperature that's holding it in?
I think we kind of go a little bit on one of those tangents now.
Oh, okay.
It's,
I like that.
no, it's good. Tangents are awesome. It's like I've said, your tangents are where creativity lies, fun stuff lies there. It's exciting. And when we don't know the answer, let's brainstorm. You know, let's think about what could be happening. Okay, I'm going to try to
I was thinking maybe the air's kind of pushed up over the mountain, and as it rises, it heats up, and then it's not really reaching the effect, like it's not reaching condensation anymore, it's evaporating again.
Yeah, it's a mechanical process. So in the valley here, we're in a kind of a, I don't want to call it a zone of low pressure. It isn't a zone of low pressure. But when the air is pushed over the mountains here, it then descends into the valley. And the valley in general has a reasonable moisture content because the lake's right there. You know, all day long, moisture has been evaporating from the lake. So there's a ready supply of moisture in that general area. But then as the air mass comes up over the mountain, it's, you know, it's whipping up over pretty fast. And then it's got this big opening here, so it descends, it naturally descends. And what's happening in this area, because of that moisture there, it's clouds are forming, but then it goes up over the mountains, it's forced to rise. You know what? That's backwards. And don't you just hate that when you're explaining something and you realize the physics of what you're explaining is backwards? I should have thought more about this because it should be the other way around. Oh, hang on, what's causing that? No. Oh, I thought this was such an elegant example until I realized that doesn't work. The physics doesn't work for that because it would be the other way around.
What would be the other way around? It should be dissipating over the other valley.
Air mass descent
Yeah.
should not cause condensation because air mass descent means the air is heating up. This is a lapse rate thing. But I don't think this is related to lapse rates and temperatures. I think it's related to the mechanical. There's a localized low pressure because it's in the valley. The wind's blasting. It's actually more complicated than I thought it was originally. I need to think about it before. But bottom line is, I don't want to bullshit you by giving you some fake explanation. But there's two things going on that I'm fairly certain of. One is the ready supply of water here. Two, there's the mechanical processes of the air mass being pushed up over the mountain and then dropping. And so it could be that this cloud's occurring here because of the local uplift here. But the only problem with that is it doesn't explain why it stays within the valley. Because local uplift here would cause clouds there. But the continued uplift over the mountains means the clouds should occur all the way over the mountains and they don't. Oh, hi, Travis. You know all about water then. What are you thinking?
Sorry, I do have a little one with me here, but my thought is perhaps because the wind is blowing over top of the water body, that air is being pushed up the mountain, and so new unmoist air is pulling up more water vapor from the lake. So it's just constantly replenishing that system. Essentially, the wind is just constantly picking up more and more moisture from the lake. So I think that's what you're seeing in terms of the building. That's really all I got to contribute at this point.
Yeah, no, thanks for that, Joe. I think you've got a point there. I think what we're seeing is some air mass mixing, right? What you've got going over the top of the mountains is air from some other location. But the air in the valley is, it's been sitting there all day long. I mean, it's been moving, it's been dynamic, but it's got a ready supply of moisture. And so the air in the valley and the air over top probably have some temperature differential, which I think is what you were referring to earlier. So the temperature differential in the air mass mixing is a part of this. And the dynamics is also a part of it. I still can't fully explain why it ends there, but there could be some wind shear effect. And if there's a wind shear effect, now we're starting to get into more atmospheric physics that is probably way beyond the scope of hydrology. But point is, it's interesting that we see these kind of phenomena. These are typical in the mountains. Air mass mixing, change in the temperature of the air leads to condensation and clouds. Anyway, I'm not going to dig myself into an even bigger hole, so we're going to move on. This is what it's all about. It's all about this curve and how we can shift air from one side of the curve to the other or back again. So this is the saturation vapor pressure curve. And again, this is stolen from 2300, geography and weather and climate. So you've probably seen something like this before. Don't worry, I'm not going to start throwing tephograms at you. But if you remember tephograms, this is simpler than that. Okay, so temperature on the bottom, minus 40 to plus 40. And then essentially what we've got on the X is moisture content. Here it's expressed as saturation vapor pressure. Over there, it's saturation specific humidity, but it is an absolute quantity of moisture in the atmosphere. Now, that is different to relative humidity, which is probably the term you've all heard of and used a lot because you see it in weather reports all the time. Relative humidity is the level of saturation in the atmosphere as observed relative to what the saturated amount would be at that temperature. And so here's a really simple equation. The actual vapor pressure equals the saturated vapor pressure multiplied by relative humidity. So that's how this axis is related to relative humidity. You need to know what the saturation vapor pressure would be, and that's this curve. And then where you are relative to this curve is the actual vapor pressure. And you can see it varies with temperature. But what we're interested in terms of cloud formation and condensation in general, is how we cross this line. Everything this side of the line, we're below saturation, so therefore we're dry or relatively dry. Everything this side of the line is saturated or vapor is condensing in the atmosphere on this side of the line, so we get cloud formation. And the further up and up and up we are on this side, or the warmer the atmospheric temperature, the more moisture the air mass can hold. So if we're on the saturated side of this curve at a high temperature, then there is a huge amount of moisture in the atmosphere. If we're on the saturated side of this curve at a low temperature, then there really isn't a lot of moisture in the atmosphere. So that's why if you take an air mass that's here, and you shift it this way, so you don't change the moisture content, you just shift it by pulling it down, it will condense, and eventually you will get precipitation. Or similarly, if you take a dry air mass anywhere under here and shift it this way, i.e. you add moisture to it somehow, then eventually you'll get condensation. So, what's happening here could be you've got an air mass over a lake, and there's a lot of evaporation going on, and just generally you're adding moisture to it, and eventually you're going to get condensation. Or here, you just get air mass mixing. Cold air mass mixing with a warm air mass is going to get you somewhere in the middle, and therefore you'll get condensation and precipitation. So cloud formation is really a function of crossing this line, crossing this saturation vapor pressure line. Now, there's one other tiny little thing that I want to add to that, and that is this slight adjustment to the curve. This is the line from the vapor to liquid phase. And then below 0 degrees C, this is the line for vapor to solid. And you can see it's a little bit lower. Or you'll get a transfer from vapor to solid below 0 degrees C at a slightly lower vapor pressure. What that means is, if you've got vapor in the atmosphere below 0 degrees C, it's actually easier for it to freeze instantaneously than it is to go through the liquid phase. It's kind of one of the quirky properties of water. It's because of the atomic structure or the atomic bonds within the crystal structure of solid water, is that when you're below 0 degrees C and more below 0 degrees C, it's much easier for vapor to just sublimate directly into the solid form than it is to go vapor, liquid, then solid. It just does it much more quickly. Now, and this is important in cold clouds that we're going to look at in a few slides time, in what's known as the Bergeron process for creating snowflakes. Now, again, I'm basically condensing a lot of 2300 into a single lecture here, but you might remember that from 2300. Okay, so how do we saturate an air mass? What are the processes of saturation? Okay, so that's the physics. What are the processes that cause us to cross that line? So we can physically add moisture vapor to the air. There's one example, waterfall. Right? You always see mists around a waterfall. That's a mechanical process of adding moisture to the atmosphere. What I've mentioned a few times, I'm mixing warm, moist air with cold air. So aircraft contrails is one example. You've got really, really hot air being jetted out the back of those engines. As soon as that mixes with cold air around it, you get instant condensation. That's why we get contrails. It is not smoke or exhaust like you see at the back of a car. It is condensation. Although a lot of the stuff you see at the back of an exhaust pipe in a car is also condensation. The steam fog is an example where you've got cold air moving across a warm water body. So this time of year, normally this time of year, if you walk by the Old Man River, you might see a layer of fog over the top. And it could be because the water is warm and the air is cold. There could be other processes leading to that, lots of different types of fog. But that's one fairly common type of fog that we'll see in the Old Man, steam fog. And then, of course, frontal systems, where you've got cyclonic activity and you've got air masses moving and encountering other air masses. They mix. And when they mix, the warmer air mass becomes colder, crosses the vapor pressure line, and we get cloud formation. And then just lowering the temperature. So one of the examples that I'm confident is right over Waterton was that at the end of the day, the air is naturally getting cooler and cooler, and so that's where we get cloud formation late in the day in many locations. And then the mechanical lifting of air masses to elevation. So what we're going to do in the next few slides is talk about some of these processes in a little bit more depth, how they actually happen, why they lead to condensation. And so lapse rates is one thing we need to understand. Again, 2300 terminology. So the environmental lapse rate, we've all come across this. This is the natural reduction in temperature as we move up through the atmosphere. So anyone that's gone on a hike in the mountains knows that you get to the top of the mountain and it's colder. And it's, it's a natural process, and it's all associated with the reduced long wave and convective heating influence in the atmosphere as you get higher in the atmosphere. It is highly variable, but somewhere between 0.6 and 0.7 degrees per 100 meters of altitude gain. Now, do not confuse the environmental lapse rate with the dry adiabatic lapse rate and the saturated adiabatic lapse rate. These are the lapse rates of a parcel of air as that parcel of air is physically moved. The environmental lapse rate is just ambient air temperature dependent. You don't need to move the air in order to encounter the environmental lapse rate. But the air does have to move or be dynamic or be expanding or contracting in order for the air mass to experience a dry or saturated adiabatic lapse rate. Now, they're different. The dry adiabatic lapse rate is greater than the saturated adiabatic lapse rate. So dry is around about 1 degree C per 100 meters, and saturated about 0.6, or pretty close to the environmental lapse rate. Now, the reason that these two adiabatic lapse rates differ is because of where the energy is going to. As the air parcel lifts through the atmosphere, the energy is being lost as it rises or gained as it drops, either as sensible or latent heat. So as a dry air parcel gains elevation, all of the energy lost is through sensible heat loss. So that's why the temperature drops very quickly. But as soon as moisture starts to condense, right? So as soon as the temperature has dropped to such a point where moisture now does condense, so that's the dew point temperature. Now what we see is any further energy loss is going into the phase change from vapor to liquid. And so therefore the sensible heat, the temperature that we observe, feel, record, is going to reduce much more slowly. Now, I just want to, these are all revision of concepts from Weather and Climate. Does this ring a bell? Okay. I should speed up, right? Because you will get all this stuff. This is really just revision. Okay, good. So air mass lifting is a critical process in all of this. And there are various ways that air mass lifting can occur. Frontal uplift, where air masses occur one another, encounter one another, and one air mass rides over another. Localized convection. So we have ground surface heating, localized low pressure lifts. Cyclonic convergence, where you've got all of the air spiraling around some central low pressure and forces lifting of the air mass in the middle. And then orographic uplift, where you've got a mechanical obstruction and air just has nowhere to go but up. Right, so these are the four major sources of uplift in the atmosphere. And all of these processes of uplift tend to lead to condensation. Right? They reduce the temperature, leads to condensation, leads to precipitation. That's why we care about these processes in hydrology. And some graphics, again, stolen from 2300, illustrating the different forms. So with cyclonic activity, we also get fronts. So the center of a cyclone is going to be a zone of uplift, a zone of precipitation. And then a cold front and a warm front are themselves going to have lift associated with them. Right? The cold front moves in and it's going to push air out of the way. Warm front moves in, rides over whatever air is in front of it. So both situations lead to uplift. Convection, of course, we've got some interesting turbulent circulations in very over localized environments. And then at much larger scales, we get this kind of cyclonic activity, and then orographic mechanical uplift there. So again, revision of concepts. Convective uplift. So we get this a lot in this part of the world, very important here in the prairie. So we'll get localized heating. As the air mass immediately above the ground surface heats up, it becomes less dense. It rises. And so eventually it's going to come to some point where it's cooled sufficiently that dew point will be reached, and then we'll get condensation formed. Dew point, incidentally, is where the actual vapor pressure equals the saturated vapor pressure, or relative humidity is 100%. Anyway, that's fairly self-explanatory. And I know you've encountered this before, but just a reminder, cold fronts and warm fronts behave differently, right? Because the colder air mass is going to be the one close to the ground. The warmer air mass is going to be the one that moves upwards. So cold fronts tend to have very, very vertical structures as they move across the land surface. So because the cold front means the cold air is behind it. So as the cold air moves forwards, it pushes warmer air out of the way. So that's why it has a very vertical face. And all of the condensation tends to occur over that vertical edge of the cold front. So cold fronts are going to be very deep, but also very short-lived. That's why if you're looking at a weather forecast and you want to plan what you've got going on for the day, sometimes we might think, oh crap, there's a cold front. That means it's kind of cold and miserable and intense rainfall. But the beauty with a cold front is it's usually gone pretty quickly. Whereas a warm front, you might think, oh, that's okay. It's going to be drizzly. It's not going to be too cold. Problem is, it could last most of the day. So I don't know, if I'm making plans for the day, sometimes cold front might actually be better to a warm front. So understand the difference between different types of fronts and how long they last and their manifestation. Not just about hydrology, it could impact your recreational plans for the day. Yeah, okay, and fronts, of course, are very often associated with cyclonic activity. And of course, when they come together, they can be occluded and things get very messy, very stormy. Cyclonic systems. Yes, I'm blasting through this very quickly. A cyclone is a zone of low pressure system. So it's in the northern hemisphere, it's going to be anti-clockwise. The southern hemisphere, it's going to be clockwise, of course. And the low pressure is in the middle because all of that air circulating around the center of the cyclone is converging in on the center. And because it's converging on the center, it has nowhere else to go but upwards. And because it goes upwards, that's why we get condensation associated with the lifting and the cooling of that air mass. Anticyclones, of course, exactly the opposite. We have ground level divergence because the air mass is spiraling down and separating at the ground level. And so because of that mechanical descent of the air mass, it's actually going to heat up. Right? So it's warming, maybe up at the upper levels, it might be at the saturated adiabatic lapse rate, but more typically, the air mass is going to descend all the way from the troposphere ground level at the adiabatic lapse rate. And so therefore, it can get pretty warm pretty quickly. Orographic precipitation. So we're very familiar with this in this part of the world. Although unfortunately, I'd say BC is probably more familiar with it than we are. But that's why there's some great skiing in the mountains here, because all of the precip gets dumped on the mountains. But the thing that's very relevant for us, of course, 50 to 150 kilometers downwind of the mountains, is that the air masses upwind are going to cool down. This is a elevation temperature graph. So on the upwind side of the mountains, there's going to be a higher moisture level. So the air mass will be forced to lift over the mountains. It will cool down at the saturated adiabatic lapse rate, which is fairly slow because it's got a high moisture content. Then we'll get precipitation, rainfall, snowfall, take a snowpack, but then as it descends on the other side, it's drier, it's lost a lot of moisture. So therefore, you don't get any latent heat exchanges occur. All of the heat increase as the air mass descends is sensible heat, no latent heat because of the lack of moisture. And so therefore, the temperature rises pretty quickly. So that's why on this side of the Rockies, it tends to be considerably warmer than on the other side of the Rockies. Not always true, but that's just a general rule. And of course, that's also where it's very dry. So it's known as the Föhn effect, but that's also a big part of why we get Chinook. Now, so looking at the manifestation of these processes in the mountains, this is flying across the Wapra ice field, so approximately north-south. So we're looking kind of to the north, that's looking east, and that's looking west. Okay, so this is the Wapra ice fields. I'm sure many of you have driven up the Icefields Parkway and seen this, except you'll have seen it from the road, and you'd be looking up at Crowfoot Glacier over here, and Bow and Peyto Glaciers over there. Now, if we turn around and look east out of the window, this is what we see. That's Mosquito Creek. So this is Bo Peak right there, and just in there is Highway 93, Icefield Parkway. But look how different that landscape is relative to this landscape. And there's only a few kilometers separating. So they were, these mountains are 3,000 to 3,500 meters. These mountains are still in that 3,000 meter range. So there's not a huge difference in surface elevation. There's a little difference, but not a huge difference. But the main difference is we're already in the precipitation shadow there. It still rains an awful lot. They still get a huge amount of snow there. But over a long enough period of time, there hasn't been enough surplus snowpack that hasn't been able to melt out on the eastern side of the valley relative to the western side of the valley. So that's why we've got glaciation here, and we don't have much glaciation there. Okay. Clouds. Now, don't worry, I'm not going to go through definitions of different types of clouds. That, again, would be a 2300 thing. So you won't get tested on anything like that. But it is important to understand that there are many different types of clouds. They all fundamentally form for the same reason, right? And that is that at that particular layer in the air, you've reached that lifting condensation level or that dew point, and water vapor is condensed to form a cloud. Okay, so they're all similar in that regard. But mechanically, clouds are very different. So where you see clouds that are very thin, you don't tend to get rainfall, right? So like stratus clouds, for example, we see them a lot in this part of the world, especially in fall. They'll get that thin layer of cloud. It might be very, very gray, but it's rare you'd get precipitation out of them because there's no vertical structure. And you need vertical structure in a cloud in order for it to create water droplets that can then precipitate out. So cumulus clouds, right, they have some depth to them. And then cumulonimbus clouds have a lot of depth to them. So that's why cumulonimbus clouds are, you know, convective clouds. They're very vertically structured because they're born out of convective processes, very rapid and strong uplift of air masses. Cumulus clouds can be derived from multiple processes, but these are the two types of clouds we tend to think about associated with precipitation. All of the rest, you know, you can get the, well, nimbostratus by definition, you can get rainfall there, because nimbo, I mean, Latin has something to do with rainfall. So anyway, you can get rainfall out of these, but it tends to be more drizzly. The more kind of stormy, intense rainfalls you're going to get out of these more vertically distributed clouds. And that speaks to the processes that's happening within the cloud before precipitation occurs. So we'll look a little bit at that. So what needs to happen in order for clouds to have precipitation? Well, the first thing to bear in mind is what it says there, is that we've got gravity acting downwards. But for anything to fall through the atmosphere, it has to have sufficient mass that when combined with the force of gravity, it can overcome the frictional opposition to gravity that occurs in the atmosphere, right? Because you've got wind movement, there's just a natural frictional resistance in the atmosphere. And so just because you've got moisture drops in the atmosphere, it doesn't mean they're going to fall to the Earth's surface. They can remain in suspension for quite a long time. I'm sure we've all walked through a cloud or walked through the fog, you know, and as you walk into it, you know, you might be bone dry, but as you get out the other side of it, you're soaking wet, but you haven't been rained on. It's just because that air mass has got a lot of saturated drops in it, but the drops themselves are very small and they're not heavy enough or big enough to actually fall under gravity. So this is the first thing we need to understand, is that for precipitation to occur, those drops have to gain sufficient mass in order for them to move under the influence of gravity. And of course, there's a lot of uplifters too. There's a lot of convection in these clouds. So if you've ever been within a cloud on a mountaintop, usually you'll see it kind of moving around. There's a lot of motion in those environments. And this motion is important for the precipitation process, because as the air is circulating upwards and downwards and sidewards within the cloud, then droplets can encounter one another. And so eventually, when the drops attain, I mean, I don't know where this statistic came from. It's out of the 2300 textbook. But when they attain a volume of 1,000 of an average cloud drop, then gravity starts to act on them. But it's not like they come flying out of the atmosphere. Then they can actually start to move down. But updraft is still going to move them around. So what's important then is we've got multiple processes by which moisture can gain sufficient mass to fall. Condensation alone is not enough. You need a condensation nuclei. Vapor is going to be attracted to that condensation nuclei, and it'll grow. So you'll get growth by condensation alone. So that's molecular vapor will be attracted to liquid water drops, and you'll get condensation. So the problem is condensation alone is rarely enough to give water drops enough mass for them to fall. So what you need is the next slide. We need to have collision and coalescence. So condensation is what starts the process. And this is why you'll get more precipitation in an environment that has more dust or more aerosols in the atmosphere. And this is how cloud seeding works. I'm sure you've all heard of cloud seeding. It's in fact, we actively cloud seed in this part of the world. And the reason for that is because we know it will increase precipitation. I think it's a little bit debatable as to how reliable it is and how much it increases precipitation, but it does work to some degree. So you've got the condensation nuclei, that starts the process, but then what really kicks the process off and leads to precipitation is the coalescence or collision coalescence. This is where drops start to encounter one another. So you've got a turbulent environment, condensation nuclei, little drops start hitting one another, they grow, they get bigger and bigger, and they continue to move up and down in the clouds through circulation. Eventually, they get big enough that they can then fall under the influence of their own mass, and that's when we get precipitation happening. But this process of drop building can occur for quite a long time in clouds before we actually get any precipitation. And you could have it happen for quite a long time. And then maybe the cloud enters into a zone where it's warmer or drier, and then evaporation starts to take over. Or even beneath a cloud. I'm sure you've all seen this. You do see it in the prairies quite a lot. Is you'll have a rainstorm up in the distance, right? And you can see it, right? You can see the rain in the atmosphere, but then you'll watch it come down. And then by the time you look at ground level, it's bone dry. It's actually hard to see it overhead. It's hard to look up at a cloud and not really fully appreciate whether the rain has started. But you can certainly see it up in the distance because you can see the cloud layer, the bottom of the cloud lifting condensation level. You can see the grayness of the moisture beneath it. Sometimes you'll see nothing at ground level. That's just because all of the stuff we've described here is happening in the clouds. Then the rain starts, but then it evaporates. So once it's out of that cloud environment, now it's into a zone of air that is warmer and drier, and it's susceptible to moving back across that saturation vapor pressure line onto the dry side. So if that happens sufficiently, rain could start but never reach the ground. And we do see that in the mountains as well. We can see that in our observational records sometimes. We're doing okay time. So I've got one slide on the Bergeron process. I thought I'd put this here because it's kind of relevant. But we'll talk about snow next week. We're not going to talk about snow today, other than how snow is formed in a cloud, and that is the Bergeron process. So remember a few slides back where we looked at the saturation vapor pressure gradient, and where we were down in the negative temperature zones. It is easier for water vapor to skip the liquid phase and go straight to the solid phase below 0 degrees C. And that's because you've got a lower saturation vapor pressure associated with ice than liquid water. And so that's what happens in a cloud that is, its full depth is below 0 degrees C. Then you will have some supersaturated moisture, and you will have some water vapor in there that is still liquid, and you'll have a lot of vapor that's still gas. But because it's below 0, the tendency is for all of that to freeze right away. So vapor is going to be more likely to transition to solid than to liquid. And so that is the Bergeron process. And so that's why you get these really ornate crystalline structures that grow very, very quickly, is because once the crystal starts, any vapor that's around it will just very rapidly attract to that crystal and grow. That's a pretty neat process. Okay. And so I guess this is where it's appropriate to explain that there are different classes of clouds. Not classes like cirrus, stratus, nimbus, cumulus, and all that kind of stuff, but classes in terms of their temperature profile. And so we have cold clouds, and warm clouds. Oh, actually, I think, yeah, sorry, I should have mentioned this. A warm cloud is not warm. We would find it cold. A warm cloud just means that from the bottom to the top, for its full depth profile, it is above freezing. And so you won't get any sublimation processes occurring in warm clouds. But then when we get to cold and cool clouds, the distinction is that cold cloud exists fully below freezing. So the bottom of the cloud is known, or it tends to be known, as a lifting condensation level. Well, that's where clouds tend to form, is at the dew point in the atmosphere. So if that level is already below 0, then that entire cloud is a cold cloud. And the reason that's important is because any circulation within that cloud is going to be susceptible to that sublimation process, or the Bergeron process. Where anywhere in that cloud, any transfer of vapor to liquid or solid is going to tend to go directly to solid. Whereas in a cold cloud, you'll have mixed processes. You'll have the regular condensation, coalescence processes of liquid, vapor liquid, but you'll also have the sublimation processes up in the top. And so in a cold cloud, this is where you can get kind of mixed processes where you'll get sublimation and crystalline formation at the top, but then as it falls down and recirculates, and liquid water could be attracted to it, and maybe you'll get hail. So a cool cloud would be, it isn't necessarily going to create hail, but it could create hail. That's why we can get hail in summertime, right? Because if the clouds are high enough or deep enough, you've got those sublimation freezing processes going on in the upper part of the cloud, but then in the lower part of the cloud, those snow crystals metamorphize and freeze into more solid clumps. and that's what we see as high. So, yeah, summertime cool clouds are synonymous with high. Oh, and very important here because of the crop insurance claims that result from that. Okay, so this speaks to something that I mentioned a couple of slides ago, is that once the rain drops have gained sufficient mass that they can overcome gravity and fall towards the earth, well, then their time is numbered, right? Because as soon as they leave, you know, the home base or the cloud, where they've been constantly nourished by 100% vapor or 100% relative humidity, as soon as they're out of the cloud, now they're, you know, they've been flattened, right, because of the moving very quickly at terminal velocity, and they've been evaporated, and they break up, which increases the surface area, which also increases the efficiency of evaporation. And so that's why, if you were able to measure the precipitation shortly beneath the cloud, and then measure precipitation as you go down, you should see that the amount of moisture at each layer would go down as you get close to the ground. Okay, so that was all atmospheric stuff. That was all 2300. Now, in the last couple of minutes of the lecture, we're going to move out of weather and climate back into hydrology. This is where the understanding of precip meets hydrology in a very kind of applied sciences context. So it's like everything before this was physics. Now we're on the applied science side of things. So we got these terms: intensity, duration, frequency. And if we understand the intensity, you know, how much rainfall in a short period of time there is, or the duration, you know, how long an event lasts, or the frequency, how often we have an event of a certain magnitude. If we understand these terms, well, for one thing, they can be mathematically quantified, and for another, we can use them in, you know, in design of infrastructure, you know, design of storm drainage systems within an urban environment, for example. So these are important attributes of rainfall events that hydrologists need to understand in order to make important decisions, you know, related to risks and water resources. So this is just an example, and forgive me that it's inches per hour, just as easily be millimeters or centimeters. The units aren't really important. But here we have a rainfall hyetograph. In your lab 2 on Monday, Linda's going to introduce you to some data that's going to look just like this. And it's for the eastern slopes here in Alberta. So this is a rainfall hyetograph. So it's the magnitude of rainfall over a certain increment of time. So in this example, these are 10-minute increments. So this gives you the intensity of the rainfall during that time period. And so here we can see for that 10-minute period in the middle, the intensity was much greater, because we had 3.5 inches per hour in that 10-minute period, whereas either side of it, we had a lower intensity. Now, another thing we can do is we can add each one of these bars and create what's known as a cumulative depth, or a mass curve. A mass curve is just synonymous with cumulative depth. So again, you'll look at this in lab 2, so you'll have a little bit more time to digest what this means, and you'll do an exercise with it. But this is the intensity plot, and this is the mass curve, or the cumulative depth plot. So these are important constructs in hydrology, and we can use this information. And I'm going to finish here. I'm going to finish on this slide. The next two aren't so important. And we can use our observations of rainfall to construct intensity duration curves. So here we have rainfall intensity. You notice it's a logarithmic plot. And then here we have duration of the event. Again, a logarithmic plot. So when we plot the log against the log, we tend to get a linear function of the intensity duration curve. And then if we plot this with time, what we see is that intensity duration every 2 years is much lower than the intensity duration that we would expect every 100 years. So this is like a probabilistic plot. And the fact that it's log-log means that the difference between this 2-year line and this 100-year line is actually very large. So at the top end, we've got 100 millimeters per hour for every 2 years. Well, that's a 50% probability in any 1 year, right? So that's what we're likely to get every 2 years. And then at the 1 in 100 year, we're at 200 millimeters per hour is our peak intensity. So it's a double. So that's a 50% probability in any year. That's a 1% probability in every year. Later on in the course, towards the end, we're going to start looking at risk assessments in hydrology, but this is where it starts: rainfall intensity duration. Okay, so that's it for today. Remember, you got another lab on Monday, and you need to hand in lab one, I think, by the end of this week. So just bear those things in mind. Have a great rest of the week. See you later. So the first 15 minutes or so, precipitation. So this is where we left off. This intensity plot. And so I started to explain it, but it was really quick. It was the end of the lecture, so I'm just going to quickly go over this again. So what we have on the x-axis is duration. So this is time. What we have on the y is rainfall intensity, or well, intensity kind of speaks for itself. The amount of rainfall in a unit of time. And then we've got these 5 different plots. The first is what we would expect every 2 years. So this is basically been aggregated over many years of data records. And this is the plot of the distribution. So 2 years, 5 years, 10 years, 25, 50, and 100 years. So what we can see is that from 2 years to 100 years, on this logarithmic intensity plot, we can see more than a doubling of rainfall intensity at the higher end. And so that's over very short durations. So 0.1 of an hour, so less than 6 minutes, so probably a 5-minute measurement interval there. But then as time increases, we see that the intensity decreases. Now, given what we learned about cloud formation and precipitation genesis in the last lecture, anyone hazard a guess as to why intensity is going to systematically decline? Question for online, assuming you can all hear me as well. So there's a pretty systematic relationship, right? We've got a log plot. And once you do the dual log, it becomes a fairly linear relationship. You can describe it by this inverse function. I'll talk about that in a minute. But the point is, this is systematic. Right? This is what is an inverse function. I'll talk about that in a minute. Process. There's some physics behind this. This isn't just some random occurrence. So as time increases, if at any given rainfall event, the intensity or the strength last week, can anybody put forward a hypothesis as to why that might be?
Because they get initial counted storage of water, and then as time goes on. You see,
When you're the storage, assuming what you available, right? When you're in process, you're utilizing water from that. Of course, we know that evaporative processes and air mass movement into moisture at a faster rate than you can add moisture back in. This is a systematic relationship, and it's because the atmosphere loses moisture as soon as it starts to precipitate. So that's correct. Now, this relationship, I is intensity, so it's not input. So those are the 2 variables we're interested in. The rainfall intensity but they're quite useful because we can use them in estimating, how long an event might last or how much precipitation we might expect with an event. And that can be useful to predict flood hazards, flood risks in certain environments. So, I mean, this on its own might not look that useful, but when water level, inundation and risks, and we're not going into that. we'll look at that more towards the end of the course. But just bear in mind that we can develop these kind of empirical relationships, and they can be useful from a forecasting point of view. Okay, so once the rainfall has left the atmosphere, hit the ground, then it's going to do something. Now we're in the domain of real hydrology. You know, what happens to the water once it hits the ground? Well, one of the first things we're going to consider as hydrologists is whether or not that water is likely to run out, whether it's likely to infiltrate. We're dealing with impervious and pervious surfaces. So impervious, it just means that rainfall cannot infiltrate. So, you know, for example, high mountain environments, bedrock geology, water falling on those surfaces like runoff. Surfaces likely to run up. And when the water hits that surface and it pools on a fairly low, that means we do have infiltration. We will have losses. Losses. Now, one thing that causes a certain amount of confusion for some people, anyway, some people don't cause any confusion, is whether or not we're these two. Why would you say? So it could be I tend to think water is involved. Often we deal with maps, and what we consider to be a lake may be a depression in the ground. And so it requires a little bit of thought. There are certain circumstances where that water, before we get to the ground, of course, if we have vegetation, we have some kind of canopy. We need to think about how that canopy is going to intercept and store and transfer atmospheric moisture to the.
Travis, yeah.
Oh, thank you. I can find that. Travis?
Hey,
Yep.
Chris. Sorry about that. I just texted you. All of us online are having a real hard time with the audio. It keeps cutting in and out, and we're only catching part of what you're saying.
Okay, well, thanks for that. Okay, well, I'll stand over here. I really do need another microphone. Does that sound any better?
Yeah, that sounds a lot better. Someone else can chime in on their end.
Yeah. Okay, well, thanks for that. What I need is one of the lapel mics, but then I can't hear any. Well, you can't hear people in the flash. Okay, so vegetation canopy, of course, intercepts precipitation before it gets to the ground. So at this point, we don't really care what's going on down here, but more often than not, where we've got vegetation, so moisture makes the canopy has a high likelihood of being able to infiltrate into the ground. Now, another precipitation, P, minus the intercepted precipitation. So a lot of P's there, but anyway. Or we can convert that into another algorithm. So this is, again, it's empirical, which means it's calibrated based on observational data. But it's useful because these parameters A and B, even though we would construct them through regression, they're very useful because A represents initial storage and B the initial storage is A and B. I mean, yes, you can derive them, right? Just get some observational data, throw that function at it and see what comes out. But in a physical sense, they actually mean something in terms of the storage capacity of that canopy. And the reason I wanted to present this, even though we've already discussed this a little bit, is just here's where we can see the systems representation. So we've got input precipitation minus output precipitation, sorry, not minus. We've got input precipitation, and the reason I wanted to present this is just output precipitation or net precipitation. We've got, and then here's where all the processes happen. And remember, we can very often refer to these processes as storages, or retention or detention storages. So we've got interceptions. And some don't really get to understand the relative proportions of these processes in this algorithm. We're really just lumping everything together as an initial loss, I, and then the proportional loss after that initial loss is satisfied. Now, this kind of approach is something you'll see in hydrology and in other areas. We can apply this kind of initial loss minus proportional loss concept in other areas of hydrology. So later on, when we start looking at hydrographs, we could apply that to almost any kind of storage. But it makes a lot of sense in the canopy environment, so that's why we're introducing it here first of all. We'll snap through these very quickly. So here's the kind of storage you can see on the needles, and immediately after a rainfall event, you can see this vapor rising from the canopy, or rather condensation once it gets into the atmosphere. So that's illustrating the evaporative and then condensation process. I think this is the last slide from the last lecture. What we're trying to illustrate here is that interception losses, whether it's that A term or that B term, are going to vary in many different ways. So first of all, interception losses will vary with whether it's rain or snow or even fog. Fog can even intercept moisture in the canopy. But rain and snow are very different in terms of their dynamics, like the mechanical dynamics of how they interact with the canopy. And then antecedent conditions. If it's very, very hot, then your losses from the canopy may be greater than if it's very, very cool, right? Because you've got a warmer surface there.
It just keeps saying that your internet connection isn't stable, so I'd say that's probably part of their problem. Yeah.
Oh, well, not much we can do about the university's internet. Yeah, okay, so antecedent conditions going to play a role, and that's true of most hydrological processes, whether your starting condition, it's hot or it's cool or it's dry or it's wet. Those are the kind of things that we mean by antecedents. So one good example is moisture. If your canopy is already, let's say, saturated, there's been a rainfall event an hour previously, and then you have another rainfall event. Well, maybe your A term has already been satisfied, and you'll get straight to the BP term. So that's an example of antecedents if it's already moist. So then there's the vegetation attributes themselves. So species, age, ecosystem type, all of these things are going to play with it. And you can still control the structure of the canopy. So it could be as simple as whether it's needles or whether it's deciduous broadleaves, or things like leaf area index. If there's a lot of foliage, then it's going to have a lot more storage capacity than if there's less foliage. So all this table illustrates here is that we've got very different values for through-fall, stem flow, and interception associated with different species. Honestly, don't worry about the species, don't worry about the values, they're not important. The point is that all of these values or these losses or through flows are going to vary with the structural dynamics of the canopy. So that's the point we're trying to get from that. Again, that was a very rapid fire end of last Wednesday's lecture. I'm going to start on snowpack, which is what today's lecture is all about. So I'm just going to present a few slides just to provide a little bit of context. So why do we care about snow? Well, we're in the Northern Hemisphere. A lot of our annual water balance, particularly in this part of the world, originates as snow. It's a very important component in storage. So the amount of snow that is stored in the mountains has a profound impact on the amount of water resource that's available for the whole year. Across the world, particularly because we don't get a whole heck of a lot of summertime rainfall here in the prairies. So it's very important that we understand the snowpack and how we observe it, how we measure it, and some of the underlying physical properties. Now, so there's a landscape you'll recognize, right? So that's just one on the other side of the valley looking across. So the reason I put this photograph up was because there's here we have some of the there's a landscape you'll recognize looking across. So the reason there's different land covers, there's other processes going on that lead to differences in snowpack distribution. So just very quickly, can somebody tell me anything they observe in that photograph that is going to influence how much snowpack is deposited or accumulated in any particular location? Anything at all?
The variability of the riparian vegetation.
Vegetation, absolutely, yeah. Aspect, yeah, you can see that over there. The terrain, yeah. Yeah. So vegetation is going to catch snow. We've got different terrain aspects where you're going to get more or less sunshine and therefore melting. And also terrain. Some areas you're going to get the deposition like deeper depths in undulations, whereas it's going to get scoured over the top of ridges. And then you can even see many little cornices forming in some of these areas. And so that's a wind-related process. So yeah, those are the kind of things that I was trying to pull out. And so when we get into Celeste's talk in a minute, you'll see how we apply some of that understanding on a much larger scale. But first of all, let's go to the biggest scale that we care about as hydrologists. Let's look at a global scale. So the aerial extent of seasonal snow cover is approximately, or just under 50 million square kilometers, and 98% of the seasonal snow coverage around the globe is in the northern hemisphere. Why is that? Online as well? Anyone tell me why that is? Why most of our seasonal snow coverage is in the northern hemisphere? Picture that globe in your head. Emily?
There's less land cover further south. And those latitudes that would have snow.
Exactly, yeah. If you look at the Earth, I mean, we've got a big blob of land cover over the South Pole, Antarctica, except that's pretty much permanently snow covered. There's very little seasonal snow in Antarctica, it's just always there. But then you go around Antarctica, well, there's a huge amount of ocean until you get to, Australia, South Africa, South America. But all of them tend to there's not a lot of land down there. Most of the land mass is in the north, where we are. So that's why most of the seasonal snow cover is in the north. And of course, that has a fundamentally important impact on the global climate system, right? Because 90% or more of the incident radiation over those snow-covered areas in winter can be reflected back out to space. So the fact that we have this seasonal snow cover means we lose a lot of incoming radiation, and it acts to keep things cool in the winter. Interestingly, when we get to springtime, all of that snow melts. And so it can take quite a while for things to really get warm. I mean, it is, right? The sunshine's peaking down, March, April, getting a lot of sunshine. But a lot of that energy, if there's snow on the ground, the energy that's absorbed at the ground surface is not going to go into raising the ground surface temperature. It's all going to go in raising the snowpack temperature and then melting it. So that's why we see a bit of a time lag in the temperatures. Because while there's a lot of snow around, the ambient atmospheric temperatures cannot get too high, simply because they have to be used in that latent heat process of melting the snowpack. Anyway, we could talk a lot more about that, but I'm going to move on. So remember last Wednesday, we looked at raindrop formation, and we mentioned that Bergeron process, which is the sublimation of vapor directly to the crystal phase that creates snow crystals. Well, just to add a little bit more to that, depending on the temperature of crystal formation, you'll get systematically different types of crystalline structures. Not something I'm going to dwell on, but if you look at those crystalline structures, it can tell you something about the temperature of the formation, so that's kind of interesting. But of course, once they start to move around and bounce off one another and go through different temperature gradients, then you'll get metamorphosis of snow grains. And to be honest, this is really what we're more interested in, not necessarily the snowflake physics. I mean, that's interesting in itself. But as hydrologists, what we're more interested in is the quantity of the precipitation, whether it's rain or snow. So just like with rainfall in radar, as you've seen before in the field lab, we can use the GeoNo. So in this case, this is a totalizing precipitation trend. I'm not going to say too much more about that. Celeste's got a little bit on that as well. And then we can also use snow pillows, which capture what's actually on the ground. So there's kind of three levels here. This is what we see in the atmosphere. That doesn't necessarily tell us what's going to reach the ground. This is what reaches the ground, but it doesn't necessarily tell us what accumulates on the ground. this is what accumulates on the ground. So these are all three different types of observation of precipitation, in this case, snow. And they're all related to one another. That's atmospheric, that's incident on the ground, and that's what accumulates on the ground. So these are important things to bear in mind, because at the end of the day, this is the one that really matters from a hydrology point of view, because this is all snowpack storage. We don't really know what's going to happen to that. You know, whether it's rain or whether it's snow, we would have to model what we think is going to happen with that, because that's just what we observe. This, on the other hand, is a storage that can persist for months throughout the winter. And this is how we measure it. So that's a snow pillow. Basically, it's a big bag full of antifreeze, and you jump up and down on it, and it'll, it's like a big squishy sponge kind of thing. But it's connected to a pressure transducer and a data logger, and so any pressure that's on top of it is recorded, and it's just basically a big weighing scale. So it measures the weight of the snow over top of it. And so there's many of these across Alberta. I couldn't tell you how many, but it's probably on the order of 100 or hundreds. I don't know, maybe Celeste knows the exact number, but there's lots of them. And they're telling us what the snowpack accumulation is throughout the winter and into the spring. So when the snow starts to accumulate, it's not this homogeneous snowpack. You know what I mean? Any of us that have played around in the snow as kids or gone skiing at a ski hill or cross country or whatever knows that snowpack has got some structure to it. Actually, where I grew up, most English kids wouldn't know that, because it's rare if we get a lot of snow. Like happens, you get a snow day and then you're playing it. And, But you guys grew up with it, so you have some intimate familiarity with snow and all of its carnations. And so the fact that we have some stratification to a snowpack is, it's not unusual. If it's been there for long enough, different weather events, temperatures, intermittent melt, wind processes are going to create this kind of structure. Now, and if you're interested in ski mountaineering and avalanches are something you want to avoid, then you're going to probably learn a lot about this, because the structure of the snowpack is fundamentally important to the safety of that snowpack and whether or not it's going to avalanche. As hydrologists, we're not as interested in that, because we're not so concerned about hazard, we're more concerned with the resource. And so the one thing, actually, I'll flip back to those in a minute. This is what we're interested in as hydrologists, is the snow water equivalent. Right? So you've got a volume of snowpack. That volume multiplied by its density is going to give you a liquid water equivalent. So you could have a 1 meter deep snowpack, but there might only be 10 to 20 or 30 centimeters of depth of water in that snowpack. So that's what we care about as hydrologists. So we've got the structured snowpack. When fresh snow falls, it's very light and fluffy, low density. But we know that towards the end of winter, especially in the spring, things start to get dense. And when you get to an isothermal snowpack, it can get heavy. When you sink into it, you're trying to drag yourself through the snowpack. It's getting wet. And that's what we mean by isothermal. The entire snowpack is 0 degrees all the way through. And now you're starting to get liquid water content in that snowpack. But before you get there, we've got wind, we've got gravity, we've got thermal processes all acting on that snowpack. And so it metamorphoses over time. So we've got these different types of metamorphosis. So constructive metamorphism is where you'll get moisture, or vapor or liquid kind of adhering to the existing crystalline structure. So you're adding moisture to the pack and it's freezing. You've got destructive metamorphism, where the individual snow grains will break down, either because they've melted and they lose moisture, or because they're abrading with other snow crystals, and so they break up. And they've got fernification, which is essentially the compaction of the snowpack, or the densification of the snowpack. And so if we take that to its ultimate extreme, you're going to get ice. That's why in glacial environments, when snow has been sticking around for 2 to 4 or 5 years, depending on where you are, eventually you'll get ice. Anything that's more than 1 year is known as firn. Anything that is ice, and it can take a few years to get to that point. I'm not going to spend any time on this. We'll talk about these kind of capillary processes in soils in a couple of weeks' time. But it is possible for snow grains and moisture to coexist. And if you get that situation throughout the entire snowpack, then it is isothermal. So here we see is just the various gradations, all the way from, air, 0% density, up to freshly falling snow, 10% or less, and then all the way through the ice in the 80 to 90% range. Now, interestingly, most of our snowpacks in this part of the world at the end of the winter are going to be somewhere in this range. Now, it could be a little bit more, could be a little bit less, but generally it's in this kind of 30 to 50% range. And that's important for us to know, because if we can measure depth and we know what density is, then we can estimate water equivalent.
Now, forgive me, I forget the textbook that I stole this from, but you'll see figures like this in many textbooks. So I'm not claiming any originality. It's just a standard figure that's out there. But what it illustrates is that there are multiple influences on snow depth or snow accumulation in general, and they all relate to the ways in which mass and energy are incident on that surface, mass being the precipitation, energy being whether that precipitation is snow or rain, and whether or not it sticks around for a very long time. So the variations in mass and energy on the Earth's surface play fundamental roles in dictating whether or not there's going to be snow present at a particular location. And then the redistribution processes. We tend to think of the redistribution processes from a gravitational or a wind perspective. Those are the two dominant ones. So once snow has fallen on the ground, it can then be displaced or moved either under the influence of gravity, like avalanches, or the influence of wind, like snowdrifts. So those are the two main processes. Now, what this figure illustrates is the different dominance of controls. And now there isn't necessarily a hierarchy here. You may think that there is, and maybe in some situations there would be, but in any given location at any given time, this may not represent the order of importance of these controls. So anyway, precipitation, is there or is there not precipitation? Clearly, if there is not, there's not going to be any snow. So that's an important one. Temperature is an index of energy. So if it's cold and there is precipitation, there's a good chance there will be snow. Latitude, as we move away from the poles, our chance of experiencing snow increases, clearly, because energy receipt decreases as we move away from the equator and towards the poles. So latitude is an important driver. Similarly, altitude, as we move up through the atmosphere, we know it gets colder. And also we tend to get more precipitation higher up in the atmosphere. And so both of those components conspire to increase the probability of snow at higher altitudes. All of these are fairly self-evident when you think about it. Once we move to these, they're perhaps less self-evident. But relief can play a role at a wide variety of scales. Relief can create its own precipitation, and it's going to play a role in terms of how snowpack is distributed on the landscape. Aspect, of course, controls energy receipt, but aspect also plays a role with regard to wind fields. So, for example, if you have a prevailing like here in southern Alberta, we have a prevailing westerly wind. So if we have a mountain chain that happens to bisect that wind field at 90 degrees or something close to it, then you're likely to have a situation where you've got more precipitation on the lee side, the windward side, whereas on the lee side, you'll get less precipitation. And the windward versus the lee side is going to vary systematically with aspect, because of its relationship to the prevailing winds. So that doesn't mean the aspect influence is always going to be the same, but it does mean that in a particular location, aspect will play a role. And then, of course, ocean distance or continentality, that plays a big role too, simply because the closer you are to the source of moisture, then the higher probability that you'll get precipitation and therefore more snow. Now, of course, we also have temporal variations. So these are kind of spatial controls, but we also have temporal controls. So clearly, when you're in polar regions, so North and South Pole, it's cold all year long, or it's cold enough all year long for water to exist in a solid state, or at least it is right now. Give it 50 years, maybe that won't be the case. Maybe give it 5 years, I don't know at the current rate, but anyway. So we get zones on the Earth's surface at high latitude and high altitude where water can remain in the solid phase all year long. Now, when you move towards the mid-latitudes, now we get seasonal snow cover. And then as we move to the equatorial zones, then we get no snow cover unless we're up on top of a mountain, like Mount Kilimanjaro, for example. Equatorial region mountain, snow-capped, but that's because it's tall. Okay, so those are kind of macro scale controls. Now let's look at some regional influences. So one that maybe we don't experience here in the prairies, but if we lived in southern Ontario, we would be very, very familiar with, and that is lake effect. So if you live downwind of a large body of water, then in winter, that body of water is going to be relatively warm, at least until it gets completely covered with ice. Now, these lakes, I believe, can get largely covered with ice in some locations and for some times, but it would be very rare that the entire lake would be ice covered because there's so much thermal energy in those environments. So for a large portion of the winter at least, they do remain ice free, and they're relatively warm compared to the air mass above them, and so they send moisture into the air mass. And as the prevailing winds, as you can see here, tend to be kind of westerly to northerly, it tends to blow that moisture-laden air mass onto the land. And as soon as that air mass hits the land, you've got frictional forces that slow it down. As the air mass slows down, it is then forced to rise, forced to lift, which forces it to cool down, and therefore it dumps its precipitation. So in these zones immediately downwind of the lakes, we tend to get a lot of snowfall. Now, similarly, we get a continental effect in ocean areas. Now, this figure is for Norway, so it's Scandinavian, it's North Atlantic, but the same would be true if this were a figure from the coast mountains in BC. And actually, if I had a bit more time, I'd try and dig out a similar figure, because I'm sure one must exist somewhere. But the nice thing about this figure is it illustrates the permanent snow and ice fields in Norway and Sweden and their proximity to the coast. So the coast is here, but also the prevalence of snow and ice for a given aspect. So what we see in all of these situations is that the quantities of snow and ice at a given altitude are greater, closer to the ocean, whereas as you go further inland, the snow line kind of increases. And so you see smaller and smaller areas of snow and ice cover further inland. So that's the continental effect. But the other interesting effect is that you get the most snow and ice accumulation on the northeast, the northeasterly aspects. And the reason in this particular case for that, well, the northerly aspect makes sense, because the reason you'll get less snow and ice accumulation on a northerly aspect is simply, well, there's less energy receipt. So, in the springtime, when snow tends to melt, these areas are going to be shaded. So even though the air temperatures might start to get warm and be sufficiently warm to melt snow, they don't get direct radiation receipt. So because they don't get direct radiation, they're in shadow, snowpack stays cooler, snowpack doesn't melt so much. So that the northerly aspect makes perfect sense, but the easterly aspect maybe is a little bit less intuitive. Now, in this particular case, the reason why easterly aspects possess more snow than westerly aspects is purely because of the wind field effect. So you've got a prevailing wind blowing across that region that is scaring the windward slopes, but then depositing snow on the leeward slopes. But scale is important here, right? Because as we can already see, if we're further inland, as we go from Norway to Sweden, once we get further inland, further to the east, we get less snow. But at the mountain scale, or the mountain and valley scale, we actually see more snow on the eastern slopes than the western slopes because of the leeward snowpack deposition process. And we'll look at that a little bit more in a minute. So relief plays a role. So we've just been looking at mountains, but at a regional kind of scale. Now, if we look at the mountain scale, the individual mountain scale, the relief or the steepness of the slopes combined with the elevation of those mountains plays a really big role. So you've got a certain elevation at which, let's say, the temperature doesn't, or the mean temperature maybe hovers around 0 degrees or is below 0 degrees. And above that temperature, you've got the potential for snowpack to last for quite a long time, maybe all year long, and maybe even become a glacier. Below that limit, maybe mean temperatures are above zero, you'll get seasonal snow, but it's not going to persist all year long. And that level, which can be variously known as the glaciation level or as the snow line, regional snow line, that varies with continentality, right? So that level itself is going to be lower closer to the coast. It's going to be higher as you get further inland. But now at an individual mountain scale, if that glaciation level is off the top of the mountain, you're not going to see glaciers there, right? So that's an altitude effect. But then also relief is very important, because the more flat or rounded, or really the less steep a mountain is, then gravitational forces won't be dominant in shedding the snow from that surface. But if you've got a really steep mountain or a steep slope, then what you're going to see is, yes, you'll get some snow sticking there, but it's going to tend to shed because of gravitational and wind redistribution. So these are kind of processes that operate at an individual mountain level. So again, this is gravity and wind effects. Okay, now looking at an individual ridge, we've all seen this. We'll see this on buildings here in an urban environment, but the classical example would be in the mountains. You've got a ridge, and you'll see cornicing on the ridges. So, I'm sure most of you have seen this before, but if you haven't, next time you go out to the ski hill, just look at the ridge lines and you'll see these. But if you've got a ridge that is kind of orthogonal to the direction of the wind, then on the windward side, you'll get compaction of the snowpack, but the snow is constantly being blown over that ridge. And then gradually you get snowpack accumulation that kind of pushes out and out and out from the edge of the ridge because of the snowpack adhesion processes. As the snow kind of builds on itself in the direction of the wind, and so it kind of bridges out, or it cantilevers out from the ridge and creates this cornice. And so I'm sure we've all seen them, where they push out several meters, and they're so big and they start to kind of curl over on themselves. And then in late spring, as things start to thaw out, this is where a lot of avalanches start, right? So on ski hills and whatever, very often you'll get the safety patrol will be blasting around the mountain, and very often it's to get rid of these cornices so that they don't create an avalanche hazard. So what this represents then is the interaction of wind processes, gravitational processes, and terrain morphology. And incidentally, that's a very localized phenomena. That's not a regional phenomena, that's very localized, very in situ. Now, as we go out in scale a little bit, now you'll notice we're kind of flipping back between scales. We're looking at regional scales, we're looking at continental scales, we're looking at micro scales. Now we're looking at something more like a landscape scale. Now this might be a few hundred meters in spatial domain. What we see at this scale is that localized depressions and canopy can play a really important role in increasing snow depth, particularly depressions. So you've got snow blowing across the landscape. You've got a bit of a depression in the landscape. That depression is going to tend to fill. It's an area of what's known as low pressure, because any depression creates its own localized low pressure. Wind will tend to go over the top of it, and anything that's within that, entrained within the atmosphere, will fall into that depression. And so the interesting thing here is, if you look at this chart of depth, it's a transect of depth across this landscape, we see that the highest depths occur in this hollow or this depression in the landscape. Now, if we also look at density, we see density doesn't vary so systematically. Now, this is interesting because even though we know density is fundamentally important in calculating water equivalent, which as a hydrologist, that's the measure we're interested in, right? Snow depth isn't that interesting, but snow water equivalent is really interesting because that tells us the water resource content. So we see density doesn't change, depth changes a lot, and we see water equivalent actually correlates with depth. So as long as we have a reasonable estimate of density, we can predict water equivalent from depth. So that's a good thing to know. We'll get to that in a minute. Okay, but this also illustrates that canopy plays a role. So we're just starting to get into that now. So snowpack interception, snowfall interception influences the snowpack at a particular location. And so the interception characteristics, the interception amount is going to be influenced by a number of different factors. One of those factors is the snow characteristic itself. Now, what I mean by that is, how warm or cold the snow is going to influence its density. It's going to influence its ability to stick to other snow grains or to stick to other surfaces. So a warmer, wetter snow is likely to stick to things better than a dry and very light snow. So the snowpack characteristics are going to play a role. Also the geometry of the vegetation. Now that can be highly variable, right? You can have shrubs, we can have tall conifers, we could have hardwood trees that have no leaves. So vegetation has got lots of different geometric characteristics. Conifers, they retain their leaves throughout the winter, so they're quite efficient at holding on to snowpack. Hardwood, for example, loses its leaves. It's got a fairly large branch area, but it doesn't tend to hold so much snow quite so easily. So the type of the vegetation is going to play a role, and the geometry of that vegetation. Now, in addition to the individual unit vegetation, the tree or the shrub, there's also the kind of the spatial arrangement of that vegetation. Now, if you've got a conifer plantation and it's very regular and very uniform, then that's going to behave differently in terms of its interception characteristics to a more natural, multi-tiered, mixed conifer hardwood canopy. Very different characteristics. I can't say how that will differ, but it's important to know that they will differ. Also, the boundary, the edge of that forest stand. Edges are very important. Edge of a forest stand is going to accumulate a lot of snowpack because it effectively traps the snow as it's blowing across the landscape. It just acts like a big wind trap, So once you get into the canopy, the wind has died down, but on the edge of the canopy, that's where all the snow gets trapped. So they're very highly productive zones of snowpack accumulation. And then, of course, once the snow is trapped on the canopy, so the upper part of the canopy, the leaves, the crown, once the snow's up there, what's going to happen to it? Well, it could stay there for the whole winter, but that's not really likely. We get wind, snowpack, the snow on the leaves, foliage, needles will metamorphose in situ. It will get denser in situ. It may become so dense or wet as it gets warmer even that it falls off. So some of the snow in the canopy will fall to the ground. Some of it will also sublimate and be lost in situ. It'll just go straight to vapor and be lost to the atmosphere. So any kind of snow interception in the canopy tends to lead to an overall reduction in snow in the water balance. If you've got no canopy, then you're going to reduce the amount of loss to the atmosphere. So it has a fundamental impact on the overall water balance. So here are some of the snow loading characteristics. So you can see how the branch and the needle structure can influence the way snowpack loads as it accumulates. This illustrates how temperature plays a role. So the warmer the branches, the warmer the air temperature, then the more flexible the branches. That has implications, right? Because if it's really, really cold, then the branches are going to be more brittle. So if you've got branches that are really cold, very highly loaded with snow accumulation, then there's a good chance they'll break. Less likely they'll break at warmer temperatures. Okay, now this plot is kind of interesting because it illustrates how snowstorm interception, or the rate of interception, varies as you increase the amount of precipitation through time. So you've got two different types of environments here. One is an old-growth forest, one's commercially thinned. I don't know anything about the characteristics of these forests other than this is going to be a fairly complex, multi-structured forest. This is going to be a fairly homogeneous and fairly open canopy. And so what we see is that with a commercial open canopy, the rate of interception is fairly low to begin with, so about 25%, whereas the more highly structured canopy might have a very efficient 60% rate of interception. But then as you go through the storm, from the early stages of the storm to the latter stages of the storm, then you'll see that the rate of interception decreases. So more than halves as you get to a higher level of precipitation. So the numbers aren't important. It's just this natural tendency for interception to decrease as a storm progresses. And the reason for that is there's a natural storage capacity of the canopy. And once you start to reach that storage capacity, the amount of additional storage that can be added must necessarily reduce. And so one way to represent this relationship in an empirical form is to use this equation. Don't worry, you don't need to memorize this equation. It's just an illustration that we can utilize empirical approaches to estimate what the snow interception rate will be for a given amount of interception. And hydrology does this a lot. There's lots of empirical calculations like this. Now, I do want to introduce energy balance, so I apologize if I'm kind of flipping through this quite quickly, but I do at least want to get into energy balance so that we can pick up on that in the next lecture. But just to kind of finish up on canopy briefly, here's a LiDAR snow depth map over the West Castle. This is in midwinter, so this is a January, February image. And this is late winter, so this is middle of April. So in this image, we've got total snow cover everywhere, but the depth is highly variable. So even in the valley bottoms, we've got 50 centimeters to a meter or more of snow. At the higher elevations, captured in these cirques, for example, we've got 3 to 10 meters in some places. So very deep snow accumulations in certain areas. But what's interesting here is if we look at this zone, there tends to be a region where we've got a fairly homogeneous and relatively deep depth of snow, and it's maybe even more obvious on this slope. And we see the same thing here. So this is late season, this is early season. Now, when we difference the two, we see that we've got this transition zone. So blues are where we've lost snow, reds are where we're still accumulating snow. So we've got this kind of pivot point, which is fairly regular all the way around the basin. Now, let's look at that a different way. So here we see snow depth. The black line represents during the accumulation phase. So this is January, February. And the gray line represents snow depth during the end of the season, once it started to melt. So we've got elevation here, we've got snow depth here. Now, the neat thing is 0 snow depths late in the season in the valley, greater snow depths up in the mountains. So that's telling us that snowpack is still accumulating at high elevation in April, right? So from here, from January to April, we've seen an increase in snow depth at the highest elevations. So that's on the ridge lines and those types of areas. Meanwhile, it's reduced in the valley. But the interesting thing is not a lot has changed here. And this corresponds to tree line. Now, it's variable everywhere, but in the castle, that tends to be about 1,800 to 2,100 meters above sea level. It's that elevation range, that 200 to 300 meter elevation range is where you get tree line. And what we're seeing is 2 important things. The first is, in both cases, this is where we get the greatest snow depths on average. The other thing that's interesting is, as we go from early season to late season, it hasn't changed a whole heck of a lot. So what that tells us is that tree line in the montane to alpine zone accumulates a lot of snow fairly quickly early in the season. Right, so you've got lots of snow up high, but it's being gravitationally and through wind redistribution processes, it's moving downslope and it's being trapped in the canopy at tree line fairly early on. And then for the rest of the winter, maybe we've reached that capacity, and maybe it's redistributed even more after that. So, but what it tells us, tree line is fundamentally important. So interception in the mountain environment is important for snow accumulation. Okay, so thus far, what we've looked at are mostly accumulation-related processes. Not a lot on precipitation, but a lot on how snowpack is distributed across the Earth's surface. Now what we're going to start to look at is melt. So everything up to now was more mass balance. We're dealing with snow as a mass. And we would look at that in a water balance context in terms of accumulating snow and then loss of snow. The loss of snow is the melt process. In order to understand that, we need to think about what is it that drives the melt. Well, it's an energy process. So this is where we start to think about that energy process.